Talking about the rank-nullity theorem, which is a theorem in linear algebra, which basically tells us this, that the dimension of V equals the dimension of the null space of T plus the dimension of the range of T. But before we can even start thinking about how to prove this, first let's just imagine a vector space V and a vector space W. And then let's imagine T is a linear transformation, which basically takes us from V to W. And these are both vector spaces, and then we can imagine a vector here, V from V, and this vector gets taken into a different vector in W, and this will be TV. So our linear transformation T takes a vector from V and puts it into a different vector in W, and this vector will be noted as T of V. So now basically there's two things that can happen. We can either have vectors in V that get sent into the zero vector in W, or we get vectors in V that get sent into just any vector in W. So, and that's what this theorem basically tells us. There's two things that can happen. Let's imagine we have a set of vectors here. So, when I draw this, it doesn't actually look like this. These are if V is a 3D space, we can imagine one line. If V is if V is a 3D space, we can imagine when I color this in like this, we can imagine one line in this 3D space. All these vectors on the line, get sent into the zero vector. But I'm just, drawing it like this so it looks easier. But let's imagine all these vectors in V get sent into the zero vector in W. So every vector here, T, is going to send into the zero vector here. This is 0. Well, then this over here, this space over here is called the null space of T. So the null space of T is is a subspace of V. Basically the null so basically the null space of T is it's a subspace of V, and it's basically every vector V from V such that TV equals 0. So it's all the vectors that V takes to 0, that T takes to 0. And then the other case that can happen is all the other vectors. So everything else, so every other vector here. So if you imagine a 3D example here, if one line, all the vectors on a line get sent to the 0 vector, then every other vector on the 2D plane gets sent into just random vectors in W. And now let's imagine we have a subspace in W here, and all of the vectors here from V get sent into this subspace in W. So boom, see here, this subspace here that I drew, it could go over the whole W, but it doesn't have to. So I'm not generalizing it. Let's say that every vector here from V that's starting the null space gets sent into this subspace in W. Well, then this subspace here, this is called the range of T. And again, so the range of T now is a subspace not of V, but it's a subspace of W, and it's defined as TV for all V's in V. So see how it's kind of interesting here. The null space is a subspace of V, and the null space of T is a subspace of V, and the range of T is a subspace of W. And basically what this theorem tells us is that the dimension of V equals the dimension of these two subspaces. So basically, we use up all of the vectors in V. All of the vectors here in V were used up. Either the vectors went into the 0 vector in T, or the vectors went into the range of T, which is a subspace of W. And you see, notice we don't have to fill up the whole W. We can imagine if V is a 2D space and if W is a 3D space, at most, if the null space of T is empty, which means it's never empty, it just contains the 0 vector, then so if the null space of T is 0, it just means it sends the 0 vector in V to the 0 vector in W. Well, then we can have this 2D plane in V gets sent into a different 2D plane in W, but we can never fill up the whole W. If W has a higher dimension than V, with a linear transformation from V to W, we can't fill up the whole W. So we can't really say anything about the dimension of W, but what we can say is that the dimension of V will equal the dimension of the null space plus the range. So the vectors either get sent to the 0 vector or they get sent into the range of T. But now, how do we actually prove this theorem? How do we, it kind of makes sense here geometrically when we showed it, but now let's go on to the actual proof. So first of all, let's find a basis for the null space of T. We know that since the null space of T is a subspace of V, well, we can always find the basis for a subspace, by some other linear algebra theorems. You can always find the basis for a subspace, and we can say that U1 to UM is the basis for the null space of T. So this is a basis for, it's a subspace in V, and these are its basis vectors. So we have m basis vectors, u1 to um. Now, all these vectors are linearly independent because it's a basis, and we know that we can extend any basis of a subspace into a basis of the whole space. So we can add, so we have these vectors, u1 to um, and then we can add other vectors, let's say v1 to vn. So we added n other vectors, and now this whole thing is a basis for v. And we know we can do that, whenever we have a basis of a subspace, we can add more vectors into that basis, and we can create a basis for the whole space. And all of these vectors here are linearly independent. We pick them in such a way that they're linearly independent because they're bases, and this is just a whole basis for v. So now we can see that the dimension of v equals m plus n, because we have m u basis vectors and we have n v basis vectors. So the dimension of v is m plus n, and we know that m, just like we know that the m also equals the dimension of the null space of t. So m equals the dimension of the null space of t, because we see that it has m basis vectors. So now the only thing we still have to show, and then the proof is over. The only thing we have to show is that n equals the dimension of the range of t. So we just have to show that n equals the dimension of the range of t. And basically the easiest way to show that is if we show, let me just do this. The easiest way to show that is to show that the range of t, so which is a subspace of w, has n basis vectors. And how we will actually show this is by showing that t v1 to t vn is a basis for the range of t. So we're going to show that these are the basis vectors. So basically it's our vectors here, v1 to vn, and we apply the linear transformation t to all of these vectors, and after applying the linear transformation, those n vectors are basis for the range of t. So how do we show that this is a basis? Well, there's first we got to show that this spans the whole this spans the whole subspace. So let's imagine we have basically for every vector v from v, we can write that v equals we can write that v equals a1 u1 am we gotta add these together, like a1 u1 plus 3 dots am then plus, let's do some other coefficients, b1 v1 plus bn vn, because we know that all the vectors u1 to um, v1 to vn, these vectors span the space v. Like we know that these vectors span v, so any vector in v can be written as a linear combination of these basis vectors. So, these are just some a1 to am, b1 to bn. These are just some scalar coefficients, and so we're writing v as a linear combination of the basis vectors of v. And now what we're gonna do is with this we're gonna see, like, we're gonna kind of manipulate this and see that this is actually a basis for the range of t. So now let's apply the linear transformation t to this vector v. So tv equals t of all of this, and we can apply t to all of these things individually. So I'm just gonna, but you see, an interesting thing that happens is tv will only equal b1 t v1 plus all the other vectors plus b2 plus b3 plus bn t vn, because where did all the other vectors go? Well, we know that all the vectors u1 to um, all these vectors are in the kernel of t, which means t sends them to the 0. We said that the vectors u1 to um are basis for the kernel, so they're a basis for the kernel. I think I said null space. It's the same thing. Kernel, null space just mean the same thing. But yeah, of the null space of t, or the kernel of t. Some people say kernel, some people say basis. Null space of t equals kernel of t. So t sends all of these basis vectors to 0, which means that this is all going to disappear. So tv just equals this. So b1 tv1 plus all of this. So, we take the coefficients out and we apply the linear transformation to all of these basis vectors. And now we can basically see that any vector, so we see that any vector in the form tv can be written as a linear combination of these basis vectors, so we can imagine as these, being basis vectors, and these b1 to bn are just coefficients. So if you picked a different v, we'd have, different coefficients. We'd maybe have like, instead of b1, we have like c1 to cn. But this t1 v1, t v1, t v2, t v, until tvn, these, always stay the same. So this is just the basis. So any vector tv, this is a vector, can be written as a linear combination of these basis vectors. So can be written as a linear combination of the basis vectors t v1 to t vn. So we know that this spans the range of t. We know that these vectors span the range of t. We just have to show that they're linearly independent, because if they're also linearly independent, that means it's a basis, and that means the basis has exactly n vectors. Because maybe if they're not linearly independent, we could get rid of some of these vectors. Maybe we only have like, from v1 to vn minus 5. We have to show that they're linearly independent, so that we actually have to use all n of these vectors. So the easiest way to show that a pair of vectors is linearly independent is to show that the only way to write the zero vector is the trivial combination, so that all the coefficients are zero. So basically, how are we going to show this? We're going to say that, imagine we have, c1 tv1 plus cn tvn. Imagine this is a linear combination, and let's imagine this equals 0. Well, then if all of these basis vectors are really linearly independent, then the only way to write the zero vectors is if all the coefficients c1, c2 to cn, if all these coefficients equal 0, then we know that these vectors are really linearly independent. Oh my god, I can't talk. So basically, how are we going to show that? Well, we can take t out, the linear transformation, because we applied it to all the vectors. So we just say t c1 v1 plus cn vn. So we can just take this linear transformation out, because we apply it to everything anyways. Just a simple algebra, and this equals 0. So basically, if t of this vector equals 0, that means that this vector is in the null space of t, or in the kernel of t. Because any vector that t takes to 0 is in the null space of t. But we also have a basis for the null space of t, and the basis is with the u vectors. So if this vector c1 v1 plus cn vn, if this vector is written in the null space of t, then we can also write this vector in a different way. Let's say with d1 u1 plus dm vm, because u1 to u this has to be u, because d1 um, because u1 to um, they're basis vectors for the null space of t. So any vector in the null space of t can be written as a linear combination of its basis vectors. And, the linear coefficients, scalars are just d1 to dm. These are just some random scalars. So there's two ways to write this vector. Basically, if this vector is really in the null space of t. But now we can quickly see, if we put all the other vectors, if we put all the vectors on one side, like c1 v1 plus cn vn minus d1 u1 minus dm um equals 0, we just put all these on the side. Well, this equals 0. Well, we know that the vectors u1 to um from v1 to vn make a basis. As we said, when we scroll up, here we said that these vectors are a basis for v, and if they're basis, they're linearly independent. So all the vectors u1 um v1 vn, the combination of these vectors is linearly independent because they make a basis for v. And the only way that a linear combination of basis vectors equals 0 is if all the coefficients c1 equals cn equals d1 equals dm, all these coefficients equal 0. That's the only way that this is possible, because they are linearly independent. So this basically told us that all the coefficients here, c1 equals c2 equals cn equals 0. All these coefficients equal 0. And that basically, so now we know that the only way to write what we wrote before, that if we have a vector here and it equals 0, the only way that this is true is if all the coefficients c1 to cn are 0, which means that these basis vectors t1 to vn are linearly independent. And now this tells us that this is truly a basis. So now we basically know that tv1 to tvn is a basis for the range of T, and so this is a basis for the subspace in W, the range of T. And now how much basis vectors do we have? We have n basis vectors. And now that's beautiful because we just proved that here what we tried to prove before, that the dimension of V equals n plus n, and we see that m is the dimension of the null space of T, which is what we showed before. And now we just showed that n equals the dimension of the range of T. So what we basically just showed is that the dimension of V equals the dimension of the null space of T plus the dimension of the range of T. And yeah, that is basically that. It's a pretty clean proof. It's a pretty important proof too. Also, just like a small side note here, because we said C1, V1, like, here we only have n basis vectors because it's from V1 to Vn, and here we have, from U1 to Um. And we're saying, like, if we're saying this is equal, does that mean n equals m? Like, not really, because these are, if we have two bases for, if those bases weren't linearly independent, you could still, let's say we have two basis vectors, this one, and we try to get to this point, so we can just take one of this and one of this, or we can have a different basis, it goes like this, like this, like this, like this. We have four basis vectors, and it gives the same vector, so, it doesn't, like, n doesn't necessarily equal m here, like, even if, but if they're linearly independent, then it has to mean that. But yeah, basically that's the proof. It's pretty it's a pretty clean proof. It's a pretty important theorem. Has a nice geometric meaning. And yeah, that is the rank nullity theorem. Oh my god, this video is way too long. Thank you for listening.